Kia ora. In this video, we're going to have a look at linear programming, which is a level 3 internal that's worth 3 credits. Let's start off with kind of unpacking what linear programming is. So linear means straight lines. And programming means following a set of conditions. So linear programming is a straight line set of conditions. So let's have a look at an example together. So in this example, we're going to own a fruit cart and we sell apples and bananas. So we need a couple of definitions to help us out. First of all, A is going to be the number of apples we sell, and B is going to be the number of bananas that we sell. Now, we know from kind of straightforward logic that we can't sell a negative number of apples and bananas. So we know straight away that A has to be greater than or equal to 0 and B has to be greater than or equal to 0 because we can't sell negative. Right, the next piece of information that we've got is our fruit cart is only able to hold 100 apples and bananas combined. So that means our apples plus our bananas has to be less than or equal to 100. And finally, we know that apples cost 50 cents to buy and bananas cost $1 each. I've only got $75 to buy the fruit. So if apples cost 50 cents per apple plus $1 per banana has to be less than or equal to 75. And I won't bother putting that in because it's much nicer just to write it like that. Now, what we're going to do is we need to find the combinations of apples and bananas that meet that criteria. Now, we could do this by hand, but we're also allowed to use Desmos. So we're going to jump into Desmos to help us out. But before we do that, we need to do a couple of things. Now, Desmos doesn't like A's and B's. Desmos prefers X's and Y's. So we're going to say that X is the number of apples that we're going to sell and Y is the number of bananas that we sell. So anywhere there's an A, I'm going to replace it with an X, and anywhere there's a B, I'm going to replace it with a Y. So X plus Y has to be less than or equal to 100. Oops, daisies. And 0.5x plus 1y has to be less than or equal to 75. So now that I've got them, let's bring up Desmos. And pop in these equations. So the first equation we've got is x has to be greater than or equal to 0 and y has to be greater than or equal to 0. So what we can see here is we've added in the red highlight and the blue highlight. So the bit that we want is that bit where the double highlight's happening, which gets very messy very quickly. So what we're going to do is instead of putting in the symbols round this way, we're going to flip the symbols round. What that means is we're shading out the bits that we don't want rather than shading in the bits that we do want. So we can see now we've got rid of all of the negatives on the red and all of the negatives on the blue. So our next equation is x plus y has to be less than 100. But remember, when we're popping into Desmos, we flip the symbol around, so greater than or equal to 100. What that's doing is it's shading out all of the bits that are over 100, which is the bits where the fruit would not fit in our cart. And then the final bit is 0.5x plus 1y has to be less than or equal to 75. So we're going to shade out the bit that's greater than or equal to 75. And that's the bit where we wouldn't have enough money to buy our apples and bananas. So what we've got now is we've got this white area. This white area is called our feasible region, and that's the points, or anywhere inside that white region would fit all of our criteria. So I could come along and say 40-40, 40 apples and 40 bananas. Well, neither of those numbers are negative, so we're okay. They add together to be 100, so they add together to be 80, so they're less than 100. And if I put it into that cost equation, I'd get $60, which is less than 75, so we know we're all okay. So what I'm going to do now is we're going to jump back in here and we're going to go across to our next page and we're going to annotate what we've got here. So first of all, this bit here we call our feasible region. Then these points here that are on the corners, these here are called our critical points. They're the points where the most interesting thing is going to be happening. So somewhere in that, on those corners, is going to be the optimal point. So let's quickly find out what those coordinates are. You can do that by tapping in Desmos. So this point here is 0, 0. This one here is 75, 0. This one is 50, 50. And this one here is 100, 0. So now that I've got my critical points and I've got my feasible region, I want to come and have a look at some scenarios. So, oops, daisies. We're going to start off with scenario 1. So in scenario 1, my apples give me a profit of $1.20. So they cost me 50 cents to buy. I make a profit of $1.20, so that means I'm selling them for $1.70. And my banana profit is $1, which means I'm selling them for $2 and making $1 profit. So let's work out at each of the critical points that we've got here, how much profit I'd be making. So 0, 0, so first of all, we need to create a profit equation. So my profit is going to be equal to $1.20x plus $1.y, because my apples were X and my bananas were Y. So now I can come along and I can put my coordinates in there. So for 0, 0, $1.20 times 0 plus 1 times 0 is a whopping $0 profit. It's probably not a good idea. 0.75, if I put that in, gives me $75 profit. This one gives me $110 profit. And this one gives me $120 profit. So if I was running this business, we should sell 100 apples and 0 bananas. Because this one here gives us our highest profit. So if I jump back to this page, this one here, we'll do that in red. This point here is where we end up with for scenario 1. Now, the next one, scenario 2, our apples profit is $1 and our banana profit is $1.20. So our profit is going to be equal to 1x plus 1.2y. So if I again pop these points into my profit equation, this is going to give me $0. This one's going to give me $90. This one's going to give me $110. And this one's going to give me $100. So under this scenario where I can make $1 profit per apple and $1.20 profit per banana, this one here becomes our optimal solution. So we should sell 50 apples and 50 bananas. So if we come back to our graph here, this one here is the optimal point for scenario 2. So in that feasible region, in that white space, there isn't a point in that scenario which would give more than $110 profit, which is that maximum profit for scenario 2. Right, now finally, let's come to scenario 3. So in this one, apples and bananas cost $1 each. To give us a profit of $1 each. So our profit is going to be 1x plus 1y. So if we come along and pop these in, this is going to give us $0. This would give us $75 profit. This would give us $100 profit. And this would also give us $100 profit. So what's happening here is both of these points here are giving us the same profit. So if I come back to my graph here for a moment, what ends up happening is anywhere along this line here ends up giving us the same profit. So that there is scenario So I could see 60/40s on that line. That would again give us $100 profit, or 80/20 that's on the line. It would give us $100 profit. So what we need to do is we need to work out how we'd word this. So what we can say is we can sell anywhere on the line between 50 apples and 50 bananas, and 100 apples and 0 bananas. To word that slightly more mathematically, the number of bananas needs to be equal to 100 minus the number of apples, because that there is the equation of that line that we highlighted, where apples is between 50 and 100. So if we were to say choose a value of apples of 80, that means our value of bananas would be 20, and that again nicely fits all of our conditions. But the last thing we need to think about is whether or not this particular scenario requires integers. Now, no one wants to buy a half brown apple that's been sitting in a fruit cart for ages. So in this particular case, we need to say, and apples and bananas are whole numbers. So what I'm going to do now is I'm just going to jump back into Desmos for a moment, and I'm going to open up one that I did up earlier. And what we've got here is this black line here is our profit equation from scenario 1. So what happens is as I make my profit smaller, I'm looking for when this line here intersects with our feasible region. So we can see that the first point here that intersects with our feasible region is that 100-0, which is where we were selling 100 apples and 0 bananas, and we can see that that was the optimal solution in that particular circumstance. If I do the same with my blue line, I can see that's coming down, and the first point that it hits, this was for scenario 2, is that 50-50. Which is, again, that optimal solution for scenario 2. And finally, for scenario 3, where x plus y was equal to our profit, if I bring this down, you can see that that purple line intersects that green line all at once. So that means that anywhere along that line is going to give us the maximum profit, which is why there are multiple solutions in that particular circumstance. So what I'd like you to do now is I want you to go and have a play with that Desmos activity. I'll put a link to it in the notes, and have a play around, see what happens as you fiddle around with things. What I'd like you to do while you're playing with it is, what would make 75 bananas the optimal solution? Can you think of a scenario with reasonable numbers, similar to what we've got? We're making about $1 profit for apples and bananas. That would make the 75 bananas and 0 apples the optimal solution. And what would make the line between 0 and 75 and 50-50 the optimal solution?